Good afternoon, my calculus students, or should I call you my calculators? Today I thought I'd give you a supplementary lesson on something called the squeeze theorem, also known as the sandwich theorem. Sandwiches. Bye, pastrami melt. All right, before I actually start with the actual squeeze theorem, let me warm you up with this inequality. Folks, this says I'm given three functions, f of x, g of x, and h of x. And the value of g of x is always between f of x and h of x. Now, what does that mean graphically? Well, it basically says this. Well, if I have some f of x function down here, I have some h of x function up here, and then I have some g of x function. Basically what it says is, no matter where I pick a value for x on the interval that I'm considering, the value of g of x will always be between the value of f of x and h of x. In other words, if I pick some arbitrary value on my x axis in my domain on the interval that I'm considering, say this is my value that I want to consider right here, this x value right here, would you agree that for the f of x function, the limit as x approaches a for the f of x function would be L. The limit as x approaches a for the green function g of x would be M, and the limit as x approaches a for the red function h of x would be N. And again, doesn't it make sense that, again, since I've told you that this green function is always somewhere in between the red function's value and the black function's value, that I know that I can assume that L has to be less than M has to be less than N. In other words, M's value, this Y value, has to be between this L value and this N value, can be greater than. Now let's suppose that I change this inequality that I'm given, f of x is less than g of x is less than h of x, a little bit. Instead of just being less than, suppose they can be equal to. In other words, g has to be greater than or equal to f's value, but it has to be less than or equal to h of x's value. Well, now what we'll see is a squeezing action. So what I could do is, instead of just having these three functions totally far apart, what would happen if I squeezed this green function with this red function and the black function? So if I started pinching in this red function this way and this black function this way, well, let's see, would this be okay for me to do? Like this? So that the red function and the black function touch right here? No, that wouldn't be good, would it? Because, again, I've stipulated up here that the g function's y values always have to lay between the f of x function and the g of x function, or the f of x function and the h of x function. So what that means is this g function, again, would have to be squeezed or sandwiched in between that red function and the black function, right? So when I look at these limits again for a particular arbitrary value on the x-axis, call it a, right? Here's the value a. I know that the limit as x approaches a for the red function would be some value, call it M. The g function, it would also have to be the same value, M, and this black function, his value for this value a would have to all be the same, right? In other words, all three of these would have to have the same limit as x approaches a. And that's what the squeeze theorem basically says, that this limit as x approaches a for all three functions would just be M. Now let's look at a more specific example, something that you guys are more familiar with. We'll start with the lower function, f of x. Let's suppose that f of x is this equation. F of x equals negative quantity x minus 4 squared plus 3. Well, if you think back to our Algebra 2 days, well, that's a parabola. It's a frowning parabola. The vertex is at 4, 3. So I'm going to go over 4 and up 3. So let's take a look at this. I want to make this red. 1, 2, 3, 4, and up 1, 2, 3. Okay, so I should have a point right there. Okay, now I need a point to the left and to the right. So I'm going to plug in a 3 for x. If I do that, I would get 3 minus 4 is negative 1, negative 1 squared is 1, negative 1 plus 3 is 2. Likewise, if I plugged a 5 in, I know I should get the same answer for my y value since there's symmetry. All right, and what I can see is I get a parabola that comes down like this. Okay. Now, if I wanted a more accurate parabola, I would have plugged in more points. Now I'm going to introduce my next function. Let's go the upper limit. Let's go with h of x. Take a look at this equation. Again, I've got a parabola here. On this parabola, I've got x minus 2 squared plus 1. In this case, I've got a vertex this time of 2, 1. If I plug in values to the right and the left of that vertex, I'm going to plug in 3. If I plug a 3 in, I get 3 minus 2 squared is 1, 1 squared is 1, 1 plus 1 is 2. Well, look at that. And with my symmetry, I've got another point over here. As you can see, I've got a parabola coming in like this, correct? All right. All right, now, let's introduce our final function, right? That function is g of x. G of x is 2x minus 4. Well, again, putting these in order, I know that f of x is my lower function, h of x is my upper function, and g of x is my smaller function, right? Well, again, if I graph this guy out, if I graphed out the g of x equation, I would get, let's see here, a y-intercept of negative 4, so 1, 2, 3, 4, and a slope of 2, so rise 2, run 1, rise 2, run 1, rise 2, run 1. Oh, look at this. As you can see, this blue graph, this line, isn't all the values on the blue line somewhere below the green values in the graph and above the red values? Except for this point right here where all three values are the same, right? Well, again, pictorially, we can see that f of x is less than g of x, which is the blue graph, which is less than h of x, which is the green graph, right? Well, if we think about this, if I set up my inequality between the three functions, okay, so explicitly written down, if I took the f of x equation, that would have to be less than or equal to the g of x equation, which would be 2x minus 4, which has to be less than or equal to the h of x equation, which is x minus 2 squared plus 1. Now, if I took the limit of each of these functions as x approaches 3, well, what would I get for each? Well, if you think about it, doesn't that mean find the y value when x is approaching 3? So I get, let's see here, negative parentheses x minus, x should be replaced with a 3. So that would be 3 minus 4 squared plus 3. Well, doing the math there, I get negative of negative 1 squared plus 3. So I get 2. Again, on the next one, plugging in a 3 for this one, I would get 2 times 3 minus 4 is 6 minus 4, which is 2 again. And again, plugging in 3 for the last function, I get 3 minus 2 squared plus 1 is 1 plus 1 is 2. As you can see, as x approaches 3 for all three functions, I get a value of 2 for my y values. And as you can see, the squeeze theorem works. Now let's take a look at what it all comes down to. Why am I blah, 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 talking? Guys, take a look at this where I can use the squeeze theorem to evaluate a function such as x squared times the cosine of 1 over x as x approaches 0. Now, the problem with this limit is, as you can see, if I plug a 0 in to this x in the denominator of this argument of cosine, I would get an undefined amount. That's no good, right? If I were to take a look at what this function looks like on the graphing calculator, I type that into the y equals screen, obviously. I'm going to adjust my window because I want to really see what it's doing as I get closer and closer to 0. So as you can notice, I'm just negative 0.01 to the left and positive 0.01 to the right of the origin. and I'm going to make sure that I'm in radians, right? I'm in radians, and now I'll take a look at this graph, all right? So when I look at this graph, take a look at what's going on here. As you can see from both the left and the right hand side, I'm getting closer and closer as I'm oscillating back and forth. I'm getting closer and closer to zero, right? Now, even though we know that the limit of a function that's oscillating usually doesn't exist, as you can see it's coming in closer and closer to zero, it looks like this limit is approaching zero, even though we know that at zero the function is undefined, right? So how can I actually show that the function actually equals zero? Well, this is where the squeeze theorem comes in. All right, so here's how we start out with the squeeze theorem. The first thing we want to do is we want to take a look at just this function cosine of 1 over x. Now remember that the cosine of 1 over x, this 1 over x is the angle that we're talking about, and we're going to be in radians, okay? Now, regardless of what angle I'm talking about for cosine, remember the cosine of any angle, right, whether it be x or 1 over x, this always has to be less than or equal to 1, but greater than or equal to -1. Agreed? Well, since that's the case, I know that this function has to be squeezed between -1 and +1, all right? And again, if you think about that, again, the graph of cosine being like this, where it will be, again, between 1 and -1, all right? Now, what I'm going to do to this is I'm going to multiply all three sides of this inequality, the left, the middle, and the right, by an x squared. By doing that, I get -x squared is less than or equal to x squared cosine of 1 over x, which is less than or equal to +x squared, right? Now, the one thing that you do want to keep in mind is that when I multiply through an inequality, don't forget that if you ever multiply or divide in an inequality by a negative value throughout, the inequality signs would have to change places. So why is that not a concern for me here? Well, again, what am I multiplying through by? Since I'm multiplying through by a squared value, I know that has to be a positive value or 0. All right, so that issue of multiplying through by a negative isn't a concern for me. Okay. All right, well, now that I've done this, I've got three new functions. I've got -x squared, I've got x squared cosine of 1 over x, which is what I'm interested in, and I've got +x squared. Again, because I know that these two, the -x squared and the x squared has to be squeezing that middle function to all the values in between it, if I look at the function x squared and -x squared, and I graph that, again, take a look at this. Here's the x squared curve. Here's the -x squared curve. Now let's type in that middle function that's supposedly squeezing. I've got x squared cosine 1 over x. And let's see if that function is squeezed between the two parabolas. I'm only doing this because it really looks beautiful to watch this. There's the x squared curve. Here's the -x squared curve. Oh my gosh. And look how beautifully this middle function, the x squared cosine of 1 over x, is being squeezed between them. Okay, now let's see if we can confirm our idea that this limit should be, of this function should be approaching 0 as x approaches 0. What I'm going to do is I'm going to take the limit of all three functions. The limit of -x squared as x approaches 0. The limit of x squared cosine 1 over x as x approaches 0. And the limit of x squared as x approaches 0. Now, again, because I've got just a plain old frowning parabola, I can plug 0 in. So the limit of -x squared as x approaches 0, I know that that's just -0 squared, which is 0. On the right-hand side, as I plug 0 in for x squared, just plain old positive x squared, I get 0 squared is 0. Well, again, because of the squeeze theorem, I know that this function, the x squared cosine of 1 over x, it has to have a value between these two values. Well, since these two values are equal, I know that this middle value must also equal 0. Hence, I've now found the limit as x approaches 0 of this function that was undefined at the value of 0. It's 0. And that's how we can use the squeeze theorem. Now again, folks, this was just for fun, just to talk about the squeeze theorem. You don't have to take notes, and you won't be responsible necessarily for this on the AP exam. Talk to you later.